Okay, so let's start and talk a little bit about retransmission protocols. We will finish that off today, hopefully. And then the coming next topics will be on medium access and so forth. We're more than half done through the course. I hope the project are progressing well. If they're not progressing well, then you need to be panicking a little bit. I'm sorry, but you need to maybe take it a little bit more seriously, because now we're running into the deadlines coming up and so forth. Okay. I don't know if you noticed, but I record now also the screen, so that's available at YouTube also if you want to just see the slideshow. It's maybe a little bit easier from that perspective. Okay. Anyway, so let's get started. Short review. We talked about the go back in at the end, and we talked about what to do to achieve maximum efficiency when transmission is error-free. The thing we want to do then is to design the send window size and the timeout according to these rules. And for a fixed frame duration TF and a fixed round trip time T0, then we can choose the size to be such that essentially you always transmit. That's the idea. That if you have a packet and the channel is available, you transmit. And then you need a window size which is large enough to support this. And then you need a timeout, that timeout should be greater than the turnaround time, otherwise we would trigger unnecessary retransmissions. So that's the lower bound of that. But you don't want to make the timeout too large, because then there are many packets to be retransmitted when there is a timeout. We'll go through an efficiency analysis to make this even clearer today, I hope. So this is what to do when there are no errors. Then this is a good choice. Then timeout doesn't matter. When there is no errors, you can set the timeout to, as long as it's long enough, that's okay. When there are errors, then you would like timeout not to be too long. And what we can do then is we can do two things. We can also increase the window size to give some robustness against lost stacks. So we add 1 or 2 packets that we can fit into this. And then we adjust the timeout accordingly. So that's what we talked about last time. So let's now move on to the next retransmission protocol that we will talk about. And if you remember, what we're trying to do now is that we went from stop and wait to go back in, because in stop and wait we spend a lot of time just waiting for acknowledgements in certain situations. So go back in solves that problem by making sure that we transmit many packets. So we have many packets that are in transit at the same time. And that works well, except when we start to get a lot of frame errors. When we get that, we trigger a lot of retransmissions, because when there is a timeout in go back in, we transmit everything which is in transit. We go back and transmit the whole send window again. So what we can do to improve things here is to also add a little bit of a buffer at the receiving end. So we can buffer packets which are received error-free but are out of order. And if we can do that, we can be smart in retransmission policies also, and only retransmit those packets which needs to be retransmitted, not those who are already being received. And that's the idea behind selective repeat. So selective repeat, we basically select what good packets to retransmit. So the main idea is that we buffer out of order error-free packets at the end, at the receiving end. So we have a buffer for that. There are many variations of this basic idea, and we will present one which is in Furusan, right? So if you read another book, you Google, you will get a slightly different description of selective repeat. But anyways, in this version, the Furusan version, the acknowledgements are not cumulative. So that means that an acknowledgement can only acknowledge one single packet, not as we didn't go back in, it was cumulative. So it acknowledged a packet and all the previous packets at the same time. So that we will see what that makes a difference in an example a little bit later. There's a single timer in this protocol as well as in the go back N protocol. The single timer here is something that you would see in other books. Maybe there is a timer per packet. You can also see that, so that's one thing that is different. And also, when the timer expires, we retransmit all the outstanding packets. So we'll see actually that there's still a gain in this. So the main idea with ARQ, just to refresh our minds, is that we have a sender and a receiver. And the sender would like to send packets over this channel. And the packets consist of a sequence number, a checksum, and then some payload. And those packets that arrive correctly are acknowledged with an acknowledgement frame that goes from the receiver to the transmitter. And that contains a ACNO. So we have a sequence number and an acknowledgement number. And then there is some logic based on what to do when you receive a packet with a certain sequence number. There's some logic in the receiver for figuring out what to do. And at the sender, you get these acknowledgements, and then you need to figure out what you want to do when you get an ACK with the ACNO, how to process that. Okay, so in selective repeat, we have a send window. And we have a send window here where the first slot here, we have a pointer to that called SF. So this is a state variable. It's the first or the oldest outstanding packet. And an outstanding packet is a packet which has been transmitted but have not yet been acknowledged. Okay, so the sender is unsure about the status of the, what should we call them, the reddish packets here. But then there is also a packet here which is grayish bluish here, and that's a packet which has been sent but has been acknowledged. So we know that this packet has arrived at the receiver. However, we don't know if this has been delivered yet or not, but it will be delivered eventually. So anyways, there is no need to retransmit this grayish packet here from the transmitter's point of view. And then there is some timer also here at the transmitter side. At the receiver side, there is also now a receive window which is has a size which is greater than 1. Because if you remember in go back N and select and in stop and wait, there is only space for one packet here. Okay, so there is no space we can buffer packets here. But here we have then a receive window, and there is a pointer pointing at an empty slot in this buffer. And this is a packet which is the next that can be delivered to the application. So this is the packet which is now currently missing. When this packet arrives, then this packet can be delivered directly to the application. This packet here, the grayish one, has been received without errors, but it cannot be delivered because then we would deliver things out of order. Okay, so this one is stored for future delivery to the application layer. To whatever high layer protocol we have. And here's another empty spot, and here's another buffer here. So what's going to happen here is that hopefully this packet will arrive, and when this packet arrives, it can be delivered, and then also this one can be delivered, and then this RN, the next to the receive, will point at the next empty slot. Okay, so that's the main idea. Okay, so in more detail, let's look at the selective repeat send window. Okay, and first of all, we remember that sequence numbers are m-bit numbers, so they need to be recycled. And then the send and receive window in selective repeat, at least in the Furusan version of it, have the same size, and that's 2 to the power of m minus 1. So if it's like, it's half of the available is in the sender and half in the receiver. We'll see what that means in a second. Okay, so what do we do at the sender here? Well, first of all, there are we need to decide what to do when we get an ACK. Okay, and if we get an ACK with errors in it, we throw it away. Okay, if we get an ACK frame which seems to have bit errors in it, we don't trust it and we throw it away. If we have an error-free packet with a certain acknowledgement number when it arrives, then we ignore it if it's outside the window of interest. So if the acknowledgement is less than SF, and what is SF? Well, it's a pointer to the first outstanding packet. So the oldest packet that we have transmitted, but not yet acknowledged. So if the acknowledgement is to the left here, we ignore it, because that only acknowledges things that we have already processed. So it is of no use to us. Now, if the acknowledgement is greater or equal to Sn, it means that it acknowledges a packet from 11, in this example, 11, 12, 13, or 14, or something like this. And these are packets that we haven't transmitted these yet. So that's obviously also bogus, right? So we just ignore that. So if the acknowledgement is such that we're somewhere in this window, then we process that. Okay? So we mark the packet with the sequence number equal to the ACK number as acknowledged. So for instance, if we get an acknowledgement for packet number 8, then we mark that as now being sorry, that was a bad example. So if we then get an acknowledgement for packet number 10, an outstanding packet, which now we have acknowledgement, we change color of this to this grayish one. It means that, okay, we have processed that. It's now no need to worry about retransmitting this anymore, because it has already arrived. If it's such that we get an acknowledgement for the packet, the outstanding packet, which is to the far left of the window, it means that we can slide it. So if ACNO is equal to SF, meaning that we acknowledge now the oldest outstanding packet, then that's great, because then we can mark this as a packet, a grayish packet now, and then we can slide the window. We can slide it to the right until we hit non-acknowledged, an outstanding packet. Right? We can slide the window to the right. And how far we can slide depends on how many of these gray packets we have after the packet which is marked with the SF here. Okay, and if it happens that we can slide empty the whole window here, that there are no more outstanding packets, that is when SF is equal to Sn, then we also stop the timer, because then there is no timeout that we need to worry about. If SF is less than Sn, there is still an outstanding, at least one outstanding packet, it could be several, then we restart the timer. Okay, so this is the logic at the transmitter side. We'll go through an example showing this in action also. But again, I urge you to look this through and justify to yourself all the steps that are done here, so you can understand what this protocol is all about. Are there any questions on the transmitter logic here? No, we're fine? Okay. Then okay, there was some hiccup here. So what do we do at the receiver? First of all, what can happen here is that we get packets, and if we get a packet which has errors in it, we throw it away. If it has no errors in it, then we check the sequence number. And if the sequence number is outside the receive window, so it's either to the left, which are packets that we have already delivered, or to the right, where these are packets that don't fit into the receive window, then we throw it away. We throw it away and we send an acknowledgement reminding the transmitter that the next one that we really would like to get is wonder if this is correct. Okay, let me check if this is actually correct. The rest I think is correct, however. If the sequence number is inside the window, what we do, then we store the packet in the receive window and we send an acknowledgement with this sequence number. And if the sequence number is equal to Rn, if the sequence number is equal to an empty slot, and it's the oldest packet that we are still waiting for, then we see we can change this from white to blue. Okay, so it's a packet that we have received, and we can deliver then packet 7, 8, 9 in this case, and then we can slide the window to start at 10 instead. Okay, so we deliver all packets that are received in order, and we adjust Rn such that Rn points to the oldest packet not yet received. Okay. Any questions on this? No? Okay, so let's look at one example to see how this works. First of all, we have 3-bit sequence numbers. That is 2 to the 3 is 8. 2 to the 3 minus 1 is 2 to the 2, which is equal 4. So 4 is the size of the send window and receive window. So they can fit 4 packets in them. Remember the calling scheme that the reddish one is sent but not not acknowledged yet, so it's outstanding. And the blue, let's call this blue, is sent and acknowledged, but it's acknowledged out of order. On the receiving end, we also have a color code. So white means not yet received, and bluish here means acknowledged but out of order. So when we start, we have a send window which is empty, and a receive window which is also empty. So SF and SN is pointing to the same packet, same sequence number here, and Rn is pointing to the leftmost here. And it's pointing to 0, which is equal to SF and SN. Okay, so now we can start. Everything is synchronized. So the first thing that happens in this sequence is that we get a request from the to send a packet number 0. We put packet number 0 into the send window. We mark that as red, which means that it's transmitted but not yet acknowledged, because at the same time we transmit packet 0 over the channel. So when packet 0 arrives here, it's put into the buffer, but since packet 0 is also equal to Rn, it means that it can be immediately delivered because it comes in order. So packet 0 is delivered to the application. The receiving window slides, so the next packet that the receiver is looking for is 1. Okay, and then it sends an acknowledgement for the packet that it just received, which is packet 0. So we see here that reception of packet 0 gets an acknowledgement of packet 0. So the sequence number and ACK number is the same. So what's happening then at the receiving end is that, okay, we get an acknowledgement, we check the acknowledgement number, and we see, okay, so that corresponds to an outstanding packet. So we mark that as now being blue rather than red. And since it's also the leftmost packet here, we can slide the window to the right. Okay, and then we're back to the same starting state, except now everything points to packet number 1 than packet number 0 as we had earlier. Okay, so this was a successful transmission of a single packet. Now, if we transmit the next packet here, or we get a request, we get a packet number 1, we put it into the send window, we mark it as red, it sends over the channel, but it's lost. Okay, receiver does nothing, of course, because the receiver hasn't received anything. We get a new request, packet number 2, we put that in the send window, we mark that as red, we send that over the channel. This packet is not received without errors, but since it's not received in order, because the sender needs packet number 1, the receiver needs packet number 1 in order to deliver the next packet in order, right? Because we have just delivered packet 0, so the next one we want to deliver is 1, not 2, but we got 2, so we put that into the send window for further processing. And then we send an acknowledgement for that packet. And if we get an acknowledgement for a packet here, the transmitter says, okay, so packet number 2 is no longer red. It goes from red to gray. Okay, marked as, okay, good, this has now arrived. No need to retransmit this. We get another packet to transmit, that's packet number 3. We put that into the send window. We mark that as red, that is outstanding. We transmit that over the channel, it's received, but it's received out of order because it's still not packet number 1, which is what the receiver is waiting for. So it puts that into the buffer and then acknowledge that. And then we go from red to gray in the send window. Okay, and then at this point in time, the next thing that happens is that there is a timeout. Okay, and when there is a timeout, the selective repeat mechanism, what it does, it looks through the send window and it retransmits all the red packets, all the packets which are outstanding. In this case, it happens to be just one, but there could be several, right? So it just retransmits this one, packet number 1, and sends that over the channel. And now, this is good news for the receiver, because now it gets packet number 1, which is exactly what it's been looking for. So it puts in packet number 1 here and sees, okay, now I have a sequence of 1, 2, and 3 of correctly received packets, and I can deliver those to the application. So the application gets packet number 1, 2, and 3 in correct order, and we slide the receiving window to now point at 4. 4 is the next packet that the receiver is looking for. And it happens also to, okay, and then it sends an acknowledgement of packet number 1 over the channel. Now the receiver here, the transmitter sees, okay, now I get an acknowledgement for 1, the only packet who I'm uncertain about its status. I change this from red to blue, and then I can slide the window and can slide it all the way to 4, because that's an empty slot. So then it slides and it's like this. Okay, so that was a fairly long example. Any questions on the logic or what's going on at different stages here? Yes?
What happens with packet number 0?
Yeah, so packet number 0, it just arrived here and it was put in here actually. So it was put in here temporarily, but since it's also the leftmost packet, it got immediately delivered and the window slided to the right. So it actually, it went in and then immediately went out, and then when the window slided. Yeah. Yes?
What is and what is that, like how you calculate S n equals 3? The first thing you did.
Oh, this one. Yeah, so the window size at both ends. So this is the window size of the transmitter and this of the receiver. And in selective repeat, when we have m bits, the size of the window is 2 to the power of m minus 1. Yeah. So in this case, we have m equals 3, so 2 to the 3 is 8. Divide that by 2, you get 4. And that is the size of the windows. So if we had, say, 4-bit here, we would have 2 to the power of 4 is 16. Divide that by 2, we get 8. So then we have 8 slots in the send window and 8 slots at the receive window.
But is m like the size of the package?
No, m is the number of bits that you allocated to the sequence numbers. And remember that the sequence numbers is in the header of the packet that you transmit, and you don't want to waste many bits on your header. So that's always constrained to a relatively small number of bits. 16 bits maybe the maximum, I don't know. Right. Okay. More questions? Okay, good. So if one wants to look this in a state diagram, finite state machine diagram instead, one can look at this. So let's see, I had one problem that I looked at. Okay, so that was actually at the receiving end. So let's see what it says here. So actually, I'm consistent with what says here. But I'm not sure if this logic actually holds. Okay, how about this? You take this with a grain of salt. It might be a typo in the book. I need to go home and think about this a little bit. Right. Okay. Anyways, otherwise I think the explanation is fine here. There was a, okay, so if you, this example, oops, sorry, I don't want to do that. This example is from figure 2310 in the book. There are a couple of typos in the book. There's some coloring of the packet here, which is wrong. So, and I believe that this one is correct. Okay, so when you look at this in the book, you might be confused. Okay. So selective repeat. I mean, the whole thing behind selective repeat was that we would like to try to make something more efficient than go back in. And the whole idea behind go back in was to make something which is more efficient than stop and wait. So what is then efficiency? Well, we talked about that, but let's recap that so we are sure exactly what we're talking about. So if we have an ARQ protocol, it resides in a layer, okay, and let's call it layer N here. I mean, it could be in the data link layer, it could also be in the transport layer, it could be in many different layers. So in Furusan in the book, all of these are described in the transport layer chapter, but some of these protocols could very well be in the data link or in both actually. So ARQ protocols are not tied to one specific layer only. They could be a different layer. So if we have layer N here, for instance, the idea is that the layer N protocol should provide a service and should provide a service to the layer above it. Okay, and that service should be error-free transmission of service data units. Okay, and it should be layer N service data units, which is the same as the layer N+1 protocol data units. This is they are actually equivalent. There is the same thing. So then the effective data rate of the service, what is that? Well, it's the rate, the data rate that the layer above us perceives. Okay. So it's the data rate which is provided to layer N+1. So how can we calculate that? Well, one way to do that is to take the number of bits in the service data unit. This is the bits, the payloads we get from above. And then we divide through with the time it takes to transmit this on the average, if you like. And that should be the data rate from above. So this is and then in bit per second, like this. Now, the layer below us is the layer that actually transmits the ARQ protocol data units. So that will be the payload plus whatever headers we put on that, and this and that, and acknowledgements and so forth. So if that has an effective rate, let's call it R. Okay, so this is the data rate of the service that I use. And RF effective is the data rate for the service that I provide. Then the ratio between these two things tells us how efficient my implementation of this service is. So the efficiency is the ratio between the effective rate, the rate that I provide, divided through by the rate that I get from below. The rate that I get from below will always be higher than what I can deliver upwards. I mean, I cannot create data rate in a layer. I can only use what I get, and I can use that as efficiently as possible. So this is the efficiency is always a number less than 1. Okay, and then to emphasize what's going on, in other words, let's go about this. I mean, here we have the ARQ protocol, right? Okay, whose efficiency we would like to somehow judge. The ARQ protocol transmits payloads and headers and receives acknowledgements back and forth here, right? And the logical connection between these two units here, on both ends of the transmission here, has a data rate which is R bits per second. Now, on the layer above it, it looks like there is a logical connection between these two entities where they are transmitting layer n service data units between them, like this. And actually, this service data units is exactly the payload that we transmit down here. Okay. Let's look at the information frame here. It consists of a header and then the payload. And the header has NO bits, O for overhead, and the whole frame has size NF bits. Okay, and then it falls that the payload bits, the number of payload bits is NF minus NO. Okay, so this is the number of payload bits, and this is the number of bits we actually transmit. Better put in this one also. Number of bits that we are actually transmitting in an information frame. And then in some protocols also the number of bits in the ACK is important. Okay. So now we nail down NF, NO, and NA. We know what rate that we can transmit the ACKs and the payloads, including headers. It's R, and we would like to calculate RF, the effective rate. So we did this for stop and wait. I won't repeat the whole thing, but the idea is that we transmit information frames. It takes a certain time, TF. There is a propagation delay. There is some processing time, and then we send an acknowledgement back. It takes some time to transmit the acknowledgement frame. There is another propagation time, and then there is some processing time. And the time between this instance, when the first bit leaves the transmitter, until the ACK has been processed, this is called the turnaround time, or round trip time, or reaction time. Okay. So for stop and wait, we transmit one frame. In the error-free case, we transmit one frame over t0 seconds. So the effective rate for stop and wait is the number of bits we transmit in the payload, which is NF minus NO, divided by t0, which is the time it takes to transmit this one. Because the transmit of the next service data unit can commence here. Okay. So the next one comes here and so forth. And then the efficiency of this can be written as this. Okay, so this we have already done. So let's now look at, this was the best we can hope for. In the green panel here, there is error-free transmission. So every frame that goes over the channel, we can decode, and every ACK that goes back, it's also error-free. So this is for error-free transmission, the best case we can hope for. What happens when we have independent frame errors? So let's look at that now. Okay, so it will be convenient to introduce a variable called NT, which is the number of transmissions it takes before a packet is delivered. Okay, so let NT be the number of transmissions needed to deliver a frame. Okay. In the best case, we only need to transmit once, right? In the worst case, we don't know. We can keep on retransmitting this frame forever, right? So the number of transmissions is either 1, 2, 3, 4, etc. It could be very, very many, right? So let's assume that frame errors occur independently. With probability PF, okay, and that acts are never lost. Okay, so what this means is that when we transmit this frame with probability PF, it will be lost. And it means that the next time we transmit this one, it will still be subject to the same probability. But if I lost one frame, it doesn't mean that the next frame is more likely or less likely to be lost. So they're independent events, right? So every time we try this out, we start over fresh. Also, we say that the acknowledgement is never lost. Okay? And the motivation for doing this, if you thought a little bit about the physical layer here, there are typically many more bits in the information frame than in the acknowledgement frame here. And if the bits are then somehow subject to independent bit errors, it's much more likely that we lose a frame. It's a higher probability of error for a frame than for an acknowledgement. So we just simply ignore this possibility. There could be, maybe this one has 1 out of 1,000 is lost, and maybe this is 1 in a million, right? So we just ignore that probability for simplicity. Anyways, the formulas that we get here are sort of approximate. Anyways, we just want to get a general feeling for what's going on. Okay, so what this means is that now we can calculate what the probability of nt being equal to some number, let's call it I. So we know that the probability that nt can take on any number from 1, 2, 3 up to no bound. Okay? And actually this follows what's known as a geometrical distribution, and it can be calculated as follows. So if nt, the number of transmissions, is equal to I, we know that the number of transmissions have been failures. Okay? And for each failure, each time we lose the frame, that happens with probability PF. And since they happen independently, to get I minus 1 consecutive frame errors has probability PF raised to the power I minus 1. Okay? So these are I minus 1 consecutive errors in a row. And then the last one was successful, and that happens with probability 1 minus PF. Okay. So that's your geometrical distribution for you. And this is true for I equals 1, 2, and so forth. Okay, so now we know the probability distribution, probability mass distribution for this random variable nt. Okay, would be different from time to time, what this is, but we know now its distribution. If we're interested in the expected value of nt, so this is the number of expected transmissions we do before we have a correct. This is the expected number of transmissions we need to do before the frame is delivered. Okay, and by definition, it's a sum from I equals 1 to infinity of the probability of that nt is equal to I times I. Okay. Luckily, one can look this up on Wikipedia or put it into something, or one can look up the formula for this. It's not very hard. It's 1 over 1 minus PF, which is intuitively correct, right? So if the probability of success is, say, so 1 minus PF is the probability of success. So say that this is 10%. Okay, then it means that the average number of transmissions I need to do is 1 over 10%, which is 10. Okay, so if you succeed on the average every 10 times, the number of trials you need to do is actually 10. So maybe this was clear from the beginning, but that's what it is. Now, what we actually will be interested is in the probability, the expected value of nt minus 1. And from this result, we can simply write this out quite right. Y is 1 minus 1 over 1 minus pf. That's the expected value of nt minus 1. And then if we then keep on calculating this, we get this to be pf divided by 1 minus pf. Okay. So now we know a little bit about this. So what is the end goal here? Well, what we would like to do is to figure out how long does it take for a frame to be delivered. If there are no errors, it's t0, right? If there are two errors, if the first one was in error, the first frame was in error and the second frame was correct, it's 2t0. Okay, if it's 3 errors in a row and then a successful, then it's 4t0. So the time it takes to deliver a frame for stop and wait, so TSW, is nt minus 1. Okay, so now there is also a timeout when we transmit the next frame. So if we say that, okay, so it's nt minus 1 times the timeout plus the transmission time for the last frame, which is t0. We'll immediately put the timeout to the smallest possible number we can because we want this to be efficient. So we put this to be equal to t0. So then it's nt. Okay, so let's not do that. Actually, let's do that soon, but not right now. So the expected time for delivery is the expected number nt minus 1 times t out plus t0, like this. The time to deliver a frame in stop and wait is a random number because nt is a random number. If we want to take the expected value of that, we take the expected value of the right-hand side here. T out is a deterministic thing. We put that outside. T0 is also deterministic. We can put that outside. And inside we have this thing. The expected value of nt minus 1, who we have already calculated to be pf over 1 minus pf. Okay, so then this is equal to then t0 plus pf 1 minus pf times timeout. Okay, so if the timeout now is selected to be equal to t0, which is the smallest reasonable number we would like to put it to, then the expected time to delivery for stop and wait is then t0 plus pf over 1 minus pf times t0, which after some calculations is t0 over 1 minus pf. Okay. So what do we know at this point in time? Well, we know we have now calculated the expected time, the average time it takes to deliver one frame in stop and wait. Okay. And what does it depend on? Well, it depends on t0, okay, and then on the error probability, 1 minus the error probability. So it's t0 divided by the success probability, if you like. So we can now calculate the effective rate. So the effective data rate we get for stop and wait is the number of bits in the information frame, which is NF minus NO, and then divided through by the average time it takes to transmit that frame, which is the expected value of TSW, which we just calculated. And then we get this to be 1 minus PF times NF minus NO divided by T0. I just divided with this one. And we see that this is actually 1 minus PF times the effective rate for stop and wait when we have 0 errors. So with the superscript 0. Because the effective rate when we did stop and wait with no errors is NF minus NO divided by T0. So what happens when we get frame errors is that we multiply the effective rate with 1 minus PF. Okay. So a sanity check, if PF is equal to 0, then we should get back the result we had in error-free. Okay, which is actually what we get, right? So this is the result for error-free. Put PF equal to 0, then the effective stop rate for stop and wait is equal to the error-free case. When we have errors, we would have less. When we have always errors, we get 0, which is also should make sense, right? We get no bits over. Okay, any questions on this derivation? So you'll get your 15 minutes, but let me just wrap this up then. So what we have done now is that we have calculated, and this the average time it takes to deliver a frame. And once we have done that, we can find the effective rate in the number of bits which are delivered divided through by the average time it takes to deliver these. That's the data rate. Okay. To get to the average number, average time it takes to deliver a frame, we need to figure out the statistics for the number of transmissions that we need to do. Okay. And that happens to be a geometric distribution. We can compute its expected value and so forth. And then we just plug that into the numbers here. And then we're done. Okay, so any questions? Now, some people feel like this is easy. Some people find this a little bit difficult. So if I ask you, how many of you thought that this was trivial? How many of you think it's incomprehensible? It's okay to raise hands, just so I know where you are, right? So I can adapt. Okay, so this is typical Swedish. Neither the extremes, right? So we're somewhere in the middle. But was this on the slow end or the fast end when it came to the derivation? How many for slow? Some. How many for fast? Yeah, all right. And then the rest is perfect, right? Okay. I just want to know, right? Because I want to spend my time and your time efficiently, right? So you can tell me also privately that you thought that this was, too fast or too slow. But let's take 15 minutes, okay?